Hey everyone, I'm Mrs. Boz. This is topic 3.1 Intermolecular and Interparticle Forces. So, our goal is to understand how we can explain the relationship between the chemical structures of molecules and the relative strength of their intermolecular forces when the molecules are of the same chemical species or the molecules are of two different chemical species. So, intermolecular forces versus bonds. Intermolecular forces are the forces between molecules that lead to a condensed state, solid or liquid. These forces are considerably weaker than ionic and covalent bonds, but add up to have significant impacts on molecular properties. So, we've already learned about intramolecular forces, which is basically like what holds um, the atoms in the molecule, right? What keeps them? They're stronger than the intermolecular forces. Um, and sorry, I'm saying this backwards. Yeah, they're stronger than the intermolecular forces. And they determine chemical behavior of the substance. They're what makes the chemical bonds, and they're categorized into covalent, ionic, and metallic bonds. So you want to make sure that you remember this, okay? So IMFs versus bonds. Okay, so we've already talked about intramolecular forces. Remember, intra basically means inside of, right? So it's like literally what's holding the molecule together versus inter, which is how they interact with each other, right? All right, so if we want to look at it like this, right? The intermolecular attraction between these two molecules is going to be weaker than the intramolecular bond that takes place between the hydrogen and the chlorine, okay? Because it's a covalent bond um, that can sometimes be seen as ionic, right? It kind of can be a little more complicated, but yes, that's the general idea. All right, so let me go ahead and move myself really quick for you guys so that you guys can see this a little bit better. So here's what's important. Intramolecular forces, the force that actually keeps the molecule itself together. Intermolecular force, the attractive force between the molecule, responsible for keeping matter in solid or liquid phase. Okay. Condensed states. Okay. Think about it, not the same as a gas. Okay. So, what do we want to know, or why does that matter? Here we go. Much like bonding, these can be seen as being on a continuum from the weakest bond to the strongest, although the features of the molecules involved will greatly impact the strength. Okay. So of course, as we look on these different little scales, right, we have these little arrows to kind of help us. All right, you have forces between the molecules, forces within the molecules. Okay. Inter, meaning the forces that hold them together. So like a water molecule to another water molecule versus intra, which is what holds the molecule, the water molecule in itself together all completely. Okay. That part does matter to be able to distinguish. All right. So make sure that you're paying attention to this scale. Okay. This is really helpful. So first is London dispersion forces. London dispersion forces exist between two covalent molecules. Remember that molecules have electrons randomly moving within them. At any given time, the location of these electrons can be such that a brief separation of charge can occur even within nonpolar molecules, creating an instantaneous dipole. So what that means is like in that moment, when we're talking about covalent, right? An instantaneous dipole would be like at that moment, it's going in a certain direction. Okay. Um, so these can affect electrons in nearby atoms, creating an induced instantaneous dipole. So you see how, like, when they're coming together, um, right, there's a little dipole, meaning the little dipole is basically the little mini thing where they come together. Okay. This is an attraction between the partial positive and the partial negative, and it's called a London dispersion force. Okay. It is important. Okay. to realize that the greater the number of electrons and the more spread out the molecule is, the stronger the intermolecular forces between them. Okay, so what this is literally saying is that the more electrons something has, and the larger the actual molecule is, the stronger the actual forces of pulling things together will be. Okay, this is because atoms or molecules with these characteristics are more polarizable than their counterparts. So think water. Okay, all covalent molecules have London dispersion forces. All. Okay, so what's important about that is that they can have more than one. Okay, and that's what's really important to know, is that you can understand that they could have more than one. All right, so dipole-dipole interactions are the intermolecular forces that result from molecules with dipole moments attracting each other electrostatically by lining up. Okay, as the distance between the dipoles increases, the strength of the attraction decreases. All right, so this is where we're talking about the actual Coulomb's law. So remember how we're talking about um, the positives and the negatives being attracted to each other, right? Like a positive Q and a negative Q come together, right? So that's what it's really saying, is those arrows represent our dipoles, right? Okay, so as the distance between them increases, the strength of the attraction decreases. Dipoles come from the partial charges in polar molecules. These forces are relatively weak when compared to bonds, only about 1% as strong as ionic or covalent, but can add up to have significant impacts on molecular properties. So we've already learned London dispersion forces for covalent molecules. So if we are to look at this as a covalent molecule, right, a hydrogen and a chlorine, because it's two nonmetals, then the way that we would want to really focus on this is that the partial positive is towards the hydrogen, the partial negative is on the chlorine, right? So there's already a dipole, meaning a arrow pointing in the negative direction of the chlorine. There's already one inside of there, right? Pointing in there, basically. And so there's automatically a London dispersion force, because there's always going to be an instantaneous dipole happening. But then you add in the fact that the negative end of the chlorine is going to be attractive to the partially positive, right? Because they're not actually negative and positive like ions, it's partial and partial. So the partially positive end of the hydrogen and the partially negative part of the chlorine are attracted to each other. And that creates a dipole, literally meaning that the end of my arrow, where I'm not having as much energy, right? Because my arrow's pointing in the long direction towards the chlorine. So the long arrow of the chlorine is attracted to the flat end of the hydrogen arrow. Make sense? Hopefully. All right, so types of dipole interactions continuing. Remember that the thing holding dipoles together is their charges. Okay, that's what literally holds them together. Even though it's sometimes temporary partial, because remember, it doesn't stay that way, because the electrons are still technically being shared and floating. It's not a complete pull away like in an ion. This charge can interact with other charges, be they full charges like in the case of ions, or temporary partial charges like in the case of the induced dipoles. These partial charges can also interact with the charge on ions, leading to an ion dipole interaction. All right, so we've now added in another type of interaction. Okay, an ion dipole interaction basically means, all right, that there is a dipole happening, right? So like this one is iodine and chlorine. There's a dipole happening there. Um, you see an actual cation, an actual cation can be attracted to the negative end of a polar molecule, which is still covalent, remember, or an actual anion can be attracted to, like negative one can be attracted, a negative ion, an anion can be attracted to the positive end of a polar molecule. Okay, so it's important to make sure that we understand that that would be an ion dipole interaction. Okay, so you've got dipole, right? Okay. And this is considered permanent dipole, by the way, because it's an actual dipole. Okay. So dipole is considered a permanent dipole. Okay. Then you've got some induced dipole interactions where they're basically between themselves, and it's kind of partial positive, partial negatives, and just kind of happening. All right. Permanent dipole where one end is definitively more positive, definitively more negative. All right. And then you've got the ion dipole possibility. Okay. So dipole, dipole, ion dipole, dipole induced dipole, ion induced dipole, and then a hydrogen bond. So what's a hydrogen bond? We'll look at that in a second. All right. So right here, they're all different types, but these are just showing us the different attractions. All right, so when comparing the strengths of interactions of dipoles and or ions, consider the following: the magnitude of the charges with the dipole, polarizability of any nonpolar species, and hydrogen bonds. So hydrogen bonds are still considered dipole, but they're a little bit different. I'm going to put myself down here and then I'll move back up in a second. Okay, they're a little bit different in that they're specifically hydrogen molecules, or sorry, molecules that contain hydrogen that are attracted to specific atoms. Okay, so a particularly strong kind of dipole-dipole force is called hydrogen bonds. These occur between a hydrogen atom, covalent bonded to a nonmetal, really important, and a nonmetal atom of a neighboring molecule. Okay, these forces are strongest with small, highly electronegative atoms, and we really only see them form between hydrogen, fluorine, oxygen, and nitrogen. So that's what's super important. You're only going to see the dipole-dipole that happens with the hydrogen bond with hydrogen, and then it's either going to be connected to fluorine, oxygen, or nitrogen. Okay. So, and that's what they're attracted to. Okay. Even though they're a relatively weak force compared to bonds, they're very important and contribute to the structure and function of many molecules. So, what that is literally telling us is that um, while hydrogen bonds are still weaker, right? Because we already said that any bond happening between molecules is weaker. Any intermolecular is weaker than intramolecular, right? But hydrogen bonds are our strongest intermolecular bond that can take place. All right. So is a summary of our forces. You've got dispersion. Every single one of them has LDF. Okay. Every single one. There's not a one that doesn't. And this is for covalent. So keep that in mind. You've got dipole-dipole. This only is going to happen between polar molecules, right? Ones that actually have dipoles. Hydrogen bonding, technically still a type of dipole-dipole interaction, but it's specifically to hydrogen bonded with fluorine, oxygen, or nitrogen, and then an ion dipole, which is a little different than what we're overall used to, but very much still possible. And those are mixtures of ionic compounds and polar compounds. And of course, those are super duper strong, but that's because they involve ions. So they're not a dipole-dipole interaction. So make sure you keep that in mind. All right. So how does this apply to any AP questions that you're going to learn? And when you're answering anything, whether it be multiple choice or FRQ, all covalent molecules have LDFs. Intermolecular forces can affect the physical properties of molecule structures, including melting points, boiling points, and enthalpy of vaporization. Dispersion forces become stronger with increasing number of electrons and elongation and must be considered in nonpolar molecules. Dipole forces are found in polar molecules when comparing substances of similar molar masses. These forces are stronger than dispersion forces. And in ionic compounds, the charge on ions is what dictates interactions with neighboring molecules. However, it should be remembered that these ions interact with the existing dipoles or neighboring covalent compounds, or can cause induced dipoles. So by the end of this unit, when you come to class, the goal is that you should be able to list all intermolecular forces present in a pure sample. Okay, meaning if I give you a sample of oxygen gas, can oxygen gas do this? It's a question. Hopefully you remember that it applies to what? Liquids and solids. Okay, but all intermolecular forces present in a pure sample like H2O. You should be able to tell me the types of bonds present. Identify and label the presence of a hydrogen bond. Compare the strength of intermolecular forces present in a sample. So being able to tell me which ones strongest to weakest in that one sample. Justify differences in the physical properties of two substances based on their strengths of the presence, IMFs present, and atomic and electronic structure contributing to those. And then use Lewis structures of two molecules to determine what IMFs exist between them and how that impacts their interaction. All right. Hopefully this helps.